Hey guys, hope all is well with you and your family. Um, this is getting a little crazy for me. I really miss all of you. I really miss being in class and having idle banter between doing physics. And I think on Thursday, perhaps let's Zoom for a little while. So on Thursday morning, let's Zoom and just check in. I'm not going to lecture or anything like that, but I just want to check in with all of you and just make sure we're all on the same page. As I see it, I will just continue to upload recorded lectures. It's virtually not much different than what I would do in the classroom at the board. The only difference is the human interaction part, which I crave. And so I certainly hope you guys miss it as well. So anyway, so here we go. This is going to finish the chapter. Just so you know, the section on capacitors in series and parallel, I will put off. I will put that off until we do simple circuits in simple circuits after next chapter. After the next chapter on current and resistance, which will start on Thursday. So that's where we are. You should be working problems from chapter 25, going through the worked examples in the text, looking at the worked examples, looking at the checkpoints throughout the chapter, all those things that I've been asking you to do since pretty much day one. So let's keep it going. Let's try to leg this thing out. First and foremost, I want you guys to take care of your families, especially your older parents or grandparents. By all means, that's the first priority, and I want you to know that. My mom's 87. I can't hold her down. She's still getting in the car every day and going out to the grocery store and buying food. And so far, she's dodged the bullet. So, but trying to get her to stay in, which is very difficult. So she's a very social being, and she's used to getting out and seeing her friends and going food shopping. Like me, she doesn't take well to being cooped up inside. But this is what we got to do, folks. All right. Hopefully, you guys in biological areas are following the data, checking out the New York Times maps of the growth of this disease, and the hope is that at somewhere along the line it's going to peter out from the actions that we're taking now. That is not interacting with other people. It's really the only way right now that we can combat this thing. Anyway, let's get into the last part of chapter 25 here. So you will recall you will recall that the capacitance for the configurations that we looked at in the last lecture can be written as epsilon 0 A over D, and this was for the parallel plate. That the capacitance was equal to epsilon 0 2 pi L, the natural log of B over A, and this was for concentric cylinders, where B was the outer radius and A was the inner radius, and so B is greater than A. And then lastly, C is equal to epsilon 0, 4 pi A times B over B minus A. And this was for concentric hollow spheres. Okay, well, I should maybe jot that down specifically. Concentric hollow spheres. Again, where A and B are the radii, B is the outer radius, A is the inner radius. And so you'll notice from these three examples, and we talked about that before, that if you look at A over D, 2 pi L over the natural log of B over A, and 4 pi AB over B minus A. Right, these all have units of reciprocal meters. Oops, I'm sorry, all have units of meters. Okay. And so in this next discussion, right, these red circled functions, right, we're just going to call capital L, so that the capacitance then can be more cleanly written as epsilon 0 times capital L. Okay, and that's just a prelude to this discussion. So we've been looking at the parallel plate arrangement for forever, it seems, right? It seems like this has been going on forever. I think we're all in the twilight zone. And so we have positive Q on the top plate, negative Q on the bottom plate. The magnitude of the charge on the plates is identical. Okay. And we know about the electric field inside the plate. We know about how to establish these charges by hooking this up to a battery, and we'll do a little review in this discussion as well. What we've been assuming all along is that the space between is filled pretty much by air. Okay? So that there's no material in there really except for air. And the first person to study this in detail was Michael Faraday. Pretty early on, actually. So Michael Faraday in 1837 investigated capacitors, and in particular, what he investigated is what happens if we no longer just keep air in between the spaces between the plates, but we actually put a material in here. Okay, so it's actually filled with some other material. And that material could be as simple as paper. Could be paper, Could be some plastics like polystyrene. Polystyrene is the material made up of those white insulating cups, which are particularly bad for the environment. Could actually be filled with water, surprisingly. Okay, and some other more exotic materials. And you can see this range of materials in table 25.1, in table 25-1 rather, in your text. And you should peruse those a little bit. So what Faraday? Now I should keep in mind. All right, we should keep in mind here that that all of this, all of Faraday's work, predated let's get rid of all this stuff here, right? Predated the discovery of the electron. Which, as some of you might recall, occurred in 1897. Which occurred in 1897. So this is actually 60 years. Michael Faraday's work was actually 60 years between the discovery of the electron. So the atomic picture of matter was not at all known to Faraday and Maxwell. And so it's pretty amazing that they were able to do the kind of work that they did, but they were. So anyway, the materials that we fill in here, right? These are sometimes called dielectrics. Right? Dielectrics, right? Which is a fancy name for insulators. Okay, so these materials were insulators or dielectrics. And what Faraday noticed, is that when he put a dielectric material between the plates of a capacitor. So this is like a bologna sandwich, right? So this is the bread, and this is the bologna or bologna. So so this is a dielectric, and what he noticed was that the capacitance, right? The capacitance increased. The capacitance increased by some factor. Kappa. And he called this the dielectric constant. Which is unitless. And so if you go to look at table 25-1, you'll see a representative list of dielectric constants. And so, for instance, things like paper have a dielectric constant of 3.5. Water, for instance, has a dielectric constant of 80. And then there's some exotic materials like strontium titanate. Strontium titanate, which has a dielectric constant of 310. So by putting these materials between the plates of a capacitor, one can increase the capacitance, in the case of strontium nitrate, by 310 times. And so that's pretty amazing, actually, because increasing the capacitance increases the amount of charge storage in some context. And so let's begin to see how that plays out. So again, by way of review, the capacitance of any configuration can be written as epsilon 0 times this function L, which is a function of just distance. So for instance, L is equal to A over D for parallel plate capacitors. And so let's look at a couple of experiments here, okay? So let's see. The first one will be where we keep the potential difference constant. I'm trying to log onto my computer at the same time as I'm talking to you. Multitasking here. And my login doesn't work. It's twice here now, so let's try one more time. There we go. So let's look at the two experiments that Faraday did. So these are Faraday's experiments. So the first one is where he kept the battery voltage constant. So here's VB, the battery voltage. And in the absence of any additional dielectric in here, we just have air. And so this would be charged up to a particular value, and the dielectric constant for air is equal to 1.00054. The dielectric constant for vacuum, that is with nothing between those plates, is a dielectric constant of 1.0 exactly. Okay, so then what he did is, again, keeping the battery voltage constant, he slipped in a dielectric. Okay, here you go. Slipped in a dielectric of dielectric constant K. So here's VB. And again, what he noticed was that the capacitance increased, which means that the amount of charge on the capacitor increased. Okay, so if you have Q here and Q prime here, then Q prime is greater than Q. The capacitor was allowed to store more charge. Remember that capacitance is equal to Q over V, right? This is being held constant. And so if this increased, then the capacitance now with the dielectric is greater than the capacitance with just air in the dielectric. And I guess some books make that C0, some make it just called the capacitance in air, and I guess I will call it that as well. And so then the capacitance is equal to then the dielectric constant times the capacitance in air, and that's worth a box. Okay, so that's worth a box. And so in general, regardless of capacitor configuration, capacitor configuration, whether it's concentric spheres, concentric cylinders, or parallel plates, the capacitance then can be written as the dielectric constant times epsilon 0 times this function of just length, which then is going to be equal to kappa times the capacitance in air. So that's regardless. It's regardless of configuration. So for any configuration, that equation will hold. Okay. So now, the second experiment that Faraday did. This time, he charged a capacitor. Right? He charged the capacitor. He removed the battery. So he charged the capacitor up. He removed the battery, and so this time he measured the voltage. He measured the voltage across the capacitor, and so this is a voltmeter, and you've used these in lab. And let's pretend the voltmeter registered a voltage, right, depicted by the arrow. And then what Faraday did is that he once again he slid in a dielectric material. He slid in a dielectric material. Okay, where are we here? Okay, here we go. He slid in a dielectric material. 1, 2, 3, 4, here we go. Now the charge can't change here, right? Because there's no battery supplying any additional charging. So he slid in a dielectric material. All right. So here we go. He put in a slab of insulator of dielectric constant kappa. And now in this particular case, right, charge is constant. Charge is constant. Unlike in the last experiment that he did where voltage was constant, this time he kept the charge constant. And what he noticed was that the voltage in this particular case decreased. The voltage decreased. So the voltage decreased. So if this is V and this was V prime, then V prime was less than V by a factor of kappa, the dielectric constant. Okay? So V prime then is equal to V divided by kappa. That's worth a box in this particular experiment. So let's try to rationalize this just a little bit. Okay, so let's look at what happens inside the capacitor when we place a dielectric there. So here's our capacitor. It's charged positively. And we know that there's an electric field that's constant and homogeneous in that capacitor. And so now let's imagine that we slide in a slab of our insulating dielectric material. Now there's two kinds of dielectric materials that we can put in, either polar or nonpolar. Okay? So examples of polar would be things like water. Things like nonpolar would be, paper or some various kinds of plastics. We mentioned before polystyrene. There's some other plastics that we can put in there, even polyethylene, which is certainly nonpolar. And so what happens in that case is that, especially in the polar case, if we were to look at the polar case, polar molecules would kind of near the surface here would become aligned. The negative end of the polar molecule would be attracted to the positive plate, and down at the other side here, the negative or the positive side would be attracted to the negative plate. And so what this would do is that it would actually form, right, an electric field which opposes the electric field set up by the plates. Okay, remember electric fields start on positively charged entities and terminate on negatively charged entities. And so I'm going to call this E prime because that's what your book calls it. Okay, and I'm going to call the electric field in the absence of dielectric E naught. And so these are both vectors. And so you can see the vector addition here would be that E prime would serve to cancel some of E naught. And so what we have then is that E is going to be equal to, vectorially is going to be equal to E naught plus E prime, right? But E prime, let's say that down is positive direction. So E then is going to be equal to E naught plus a negative. Actually, let's get rid of these guys. Okay, E prime. And so then the electric field overall is going to be reduced. The electric field will be reduced. Okay. And again, this is assuming that kappas are greater than 1, which if you look at table 25-1, they are. Okay. So the dielectric also weakens the electric field. And this happens for both polar and nonpolar materials, because even for nonpolar materials, when you put them in an electric field, an induced dipole is set up, which again will generate an electric field that is opposite to the direction of the electric field inside the plates. So, so the dielectric will also weaken the electric field. So we will then skip 25-6, which looks at Gauss's law in dielectrics with capacitors with dielectrics. And the next time we meet, we will move on to chapter 26. So next will be chapter 26, current and resistance. Beautiful. All right. Again, I wish you all well, and we'll communicate directly on Thursday. All right. You guys take care. All right. Bye-bye.